You mentioned that there are various types of accelerators, such as the proton-proton, proton-electron, electron-positron. Now, what are the differences between those? What will they do for you, quite apart from the technology? Well, what does the proton-proton do for you as opposed to electron, positron, and so on?
Yep.
You want me to
would you like to take that? Yep.
Yep. Okay. Is the mic on?
Yes.
Yeah, okay. So, I mean, in a way, there isn't really a dispute among us, I think, because the different facilities that have been discussed here have different pluses and minuses in terms of their ability to attack new physics, which is what we're really trying to get at. And so they're complementary in many ways. So, as Frank correctly said, it's easy to accelerate protons compared with electrons or positrons in a big ring because they don't emit synchrotron radiation in the same way because they're much more massive. The problem is, so you can get proton beams to very high energies, but when you slam protons into one another, protons are not elementary particles. They're bags of quarks and gluons, and so a little bit of one proton will hit a little bit of another proton, and they will scatter from one another. So although you have very high beam energies, the energies of the interacting particles typically are very much lower than the maximum beam energy available because it's a bit of one proton that's hitting a bit of the other, and then you have the rest of the proton, which causes a mess. So in fact, the center of mass energy of a proton-proton machine, the effective center of mass energy is not as high as the beam energy written on the tin. It's roughly an order of magnitude lower than the notional twice the beam energies. And then you have a lot of backgrounds, but you can get the beams to really high energies using that technique. With electrons and positrons, those are fundamental point-like particles, and so when an electron and positron annihilate, you just get the energy. That energy condenses into the new things. You know everything about the collisions because the momentum is zero and you can measure the energies of the beams coming in. And so you have a complete understanding of the kinematics of these interactions. And so when you make Higgs particles, for example, there's the Higgs boson and a Z boson in the final state and nothing else. So from an experimental point of view, they're really quite complementary ways of attacking the physics. And of course, the physics is the same for all of us. It's the physics of top quarks, Higgs bosons, dark matter, supersymmetry, or whatever it may be out there. So is that a sort of a first clue as to some of the differences in what these things do? Pluses and minuses of all these different techniques.
So I sometimes say with that as well that the hadron machines are kind of discovery machines. They, because of that mix-up of momentum, you can get all kinds of stuff flying out, whereas the electron and muon machines may be more precision machines. Is that?
Another analogy, I don't know if it's helpful, is that these very high-energy proton-proton machines, they're instruments which give you a very broad field of view. So there's a lot going on, and you have a big landscape, and you get a look at the landscape. And then when you've realized that there's a mountain in the distance in the landscape, a Higgs boson, for example, you want to home in with a precision microscope. And that's where an electron-positron machine is exactly the instrument you want to make Higgs bosons and nothing else.
Can I make?
Yes, go ahead.
So this is absolutely correct, of course. So just 2 points to pick up at the end. So once you've scanned the landscape, it can be that the nature that you're looking at has a particle in it which has a quantum number of an electron as well as a quantum number of a quark. And that would be a real motivation for doing an electron-proton collider because you're putting those two things together and you see what comes out. In the muon case, you've got one extra piece, which is that it makes neutrinos. There isn't a theory that describes the neutrino, and therefore you're studying, using the neutrinos directly, you're studying physics which is not described in the standard theories, the standard model. So you have a path there that you can now articulate where you can start small and grow big. So that's an extra piece.
Okay. Yep, there's loads more questions popping up. I think this gentleman was first. If we can have a microphone over this side. Thank you.
Thanks very much for great talks. In the battle between the linear and the circular collider between Frank and Phil...
Complementary battle, which is...
Obviously, there's a technological barrier in terms of the superconducting magnets. And Frank did mention it in passing that There has been some sort of proof of concept, but really that's not completely sorted out yet. And there will need to be a technological shift in the magnets to get up to the higher, to 100 kilometres in terms of. And I wonder whether, getting a feel, is the ILC ready, effectively technologically ready to go? And could we, apart from funding, obviously, are we ready to look at the Higgs mechanism with that?
So maybe I'll let Frank address the magnet question quickly first, and then maybe Phil.
Yeah, we are quite lucky with the magnets because we have this high luminosity LHC upgrade, which I showed, which will come in the early 2020s. And for that upgrade, we need about 40 superconducting magnets with based on the new technology already. Not with 16 Tesla field, but with around 12 Tesla field. So there will be a rather large-scale use of such magnets already as a next step of the LHC upgrade. And that will be the step that is needed to go from there to the production of thousands of magnets for the next collider. But we will use several tens of these magnets in the upgrade of the LHC, and that is an approved project, and the prototypes, they're working beautifully with a peak field above 12 Tesla.
So by the time that project's done, that technology is demonstrated, that's ready, right?
Not at 16 Tesla, but at somewhat lower field,
right?
but it's a new technology that is demonstrated at 50% higher field than the LHC magnets. Yeah. So that's a very important step in the evolution to the next collider.
So about the technology readiness of ILC?
So, we promised Suzie that there would be no fisticuffs on stage.
They promised me, not on camera.
So we will maintain that rule, but you may have wondered about the order of the presentations, and they were, of course, ordered in maturity. So that is to say the maturity of the technology, not the maturity of the speaker. So the International Linear Collider has a 10% scale model prototype that is sitting there in Hamburg that has been built. The technology has been built in industry, mainly European industry, as a matter of fact. It's not magnets in this case, it's the superconducting niobium radio frequency accelerating technologies, the things that we need to provide the 30-odd megavolts per meter that Stuart introduced to actually get the particles up to high energies. There are 100 of these modules sitting in a 2-kilometer tunnel in Hamburg. They'll be beaming that machine by the end of this year. That is roughly 1/16 of the entire number of modules that we would need to do the real International Linear Collider. It's there, it's ready to turn on. It's a 10% scale model. The technological issues have been solved. The technology has been industrialized. So we really believe that that is a shovel-ready project, and we are waiting for our Japanese colleagues, hopefully, to give the green light.
Okay. There was another question up the back on that side as well, if we can.
Thank you for a very interesting talk. I've got 2 questions. One, if muons are so great, why not use towels? And 2, the plasma thing, can you actually get something from one end to the other without it hitting something in the middle? Or is that one of the problems?
Let's tackle those one at a time, shall we? So why not towels, Ken?
So the tau is heavier, 1.7 GeV or so, compared to the muon, which has 106 MeV. So it's order of magnitude or more difference. The rate of decay is going as some power of the mass. So the lifetime of a tau is way smaller than it is of a muon. And then because it's heavy, it's also more difficult to produce. So you get a lower rate when you produce them, and they decay more quickly. Which means that the intensity of the beam decays more quickly. So much, much harder. There's one more. So the advantages you would get in the synchrotron radiation, all of that, would be better because they're heavier. The disadvantages, because it's so heavy, it decays into all sorts of things. So you cannot do the neutrino science with it because it decays into too many things. So you don't get the clean nu E, nu mu beam out of the tau.
Okay, and the second half of that is so the question was kind of, can you get a beam out of the thing without ruining your accelerator? Is that kind of the question? Yeah, I'm getting a nod.
Well, so you would talk, maybe I could paraphrase your question, which is, if we can make something that's got a 10,000 megavolts per meter, why don't I just make a meter-long plasma accelerator and
We're all
and
going.
do that.
We're going
Yeah?
home.
Yes.
Yeah.
And then these guys will go home.
Can write a paper after this.
So there are some real problems with it, actually. So not problems, but one is so the way that's been done so far is to drive this to create a wave that charged particles can surf on inside the plasma. And to do that, you need to sort of send something through the plasma to create a wave in its wake. That's why it's called a wake field. So it's traveling behind the driver. And so one of the most successful ways that that's been done so far is using a laser pulse to drive it. Now, these relativistic particles all travel at basically the speed of light. So it's 99.9999% of the speed of light. The problem with a laser is as soon as you put light, which travels in vacuum at the speed of light, as soon as you put it into a medium, it travels a little bit slower than the speed of light. And so when I do that in a laser plasma accelerator, my driver is traveling a little bit slower, maybe 99.9% of the speed of light. So pretty close. But that difference between 99.9 and 99.99999 is enough that the electrons are actually traveling faster than the wave, which goes at the same speed as the laser pulse. And so just like a surfer on a water wave starts at the top of the wave and ends up at the bottom, and once he's got to the bottom, he can't gain any more energy, that's exactly what happens in a laser-driven plasma wave. So we start at the top of the potential, and we actually drift down it, and once we get to that point, we can't gain any more energy. And so the maximum energy that people are getting in a single stage of acceleration is limited by that process. So that's why, even though it's 10,000 megavolts per meter, the limit is only 4 GeV in less than 10 centimeters. There are some ways around this. There are some really key ways around this. Okay, so one of the most obvious ones is you just build another one. Okay, so that you got to 4 GeV in 10 centimeters. Somehow you have another laser pulse and you have another 10 centimeters and you get up to 8 GeV and you keep doing that. So you can do that and you can look at the numbers and still, as long as you don't have too much space in between these modules, then your average accelerating gradient is still much better than the conventional ones. There are many issues with that, many technical problems with that as well. Another way of doing this, and this is quite cool, is I mentioned that we use lasers to drive the plasma wave, but the problem is with a laser is it travels a little bit less than the speed of light. But a charged particle beam at high enough energy is traveling at the speed of light. And actually, as a charged particle beam, if it's intense enough, travels through a plasma, it also drives this wave, this plasma wave that will accelerate it. And some very successful experiments have been done on SLAC over the last 10 years or so, where they've used the electron beam and the positron beam for some of the experiments to drive a plasma wave and accelerate some particles from that. And they've been doing some great stuff. I think one of the sort of key headline results happened a good few years ago, which was where they took before SLAC was turned into an X-ray machine, they took the 40 GeV electron beam, so it's got taken 2 miles, it's got to 40 GeV, and then they put it into a meter-long plasma. That beam drove a plasma wave. Most of that beam slowed down because its energy was lost into driving the plasma wave. But right at the back of the plasma wave, the back of the beam was sitting in the accelerating part of the plasma wave, and it doubled in energy in a plasma that was just a meter long. So it was only it wasn't a nice quality beam, but it really demonstrated that these plasma waves have a huge potential. So 2 miles to get up to 40 GeV and another meter to get up to 80 GeV. And so I'm a laser Wakefield guy. That's what I specialize in. But I don't want to put too much money on it. But I think if you really want to go for the high energy frontier, so the particle colliders, I think maybe the beam-driven stuff has a bit of an edge on that. So hopefully that was useful.
Okay, thanks. Are there more questions at the moment coming from up here? Yep, there's one right up the back there.
Hi, thank you very much for amazing talks. I just had a question for Professor Zimmerman. Sorry, it's late. You talk like accelerators have expiry dates on them, as in they only last a certain amount of time and then we have to build a new one. I was just wondering, why is that? Does the technology just become obsolete, or do they wear out and become dangerous to use? Or, yeah, sorry, it's probably a stupid question, but...
Did you get the question?
Yeah. Why do the accelerators have a lifetime?
Yeah. So do they have a physical lifetime, or is it something else? Is the reason why we're wanting to continually build new ones? To paraphrase your question. Yeah.
I guess the physics program ends at some point. You produce a certain number of data, and you try to increase the data rate by improving the performance. And at some point, you reach a limit, and then you can run at the maximum performance. For example, limit could be the cooling of the accelerator or the RF power. So you reach some limit in intensity and a limit in the data rate that you can produce. And then it becomes uninteresting for the particle physicist after a while. If you collect 10 years of data, then running another 10 years just doubles the number of data, so it gives you a factor square root in the statistics. So at some point, it takes too much time to improve the statistics. So then at that point, you like to have another accelerator. Either you improve the performance by an upgrade, like the high luminosity LHC, it gives you a factor 10 in the data rate, so that you can double the amount of data in 1 year or so instead of waiting 10 years. And then in the end, we have seen basically the physics at that energy range, and we like to go to higher energy. It's more interesting, at least for the hadron collider, it's more interesting to go up in energy again. When you go up in energy, you also produce a lot more events at low energy, because you have these constituents, the quarks and gluons, which collide. By going up in energy, we also produce a lot more Higgs particles, for example. Some small factor in energy gives you 1 or 2 orders of magnitude more Higgs particles per second. So you gain in the energy reach, and you also gain at low energy when you increase the energy.
I think Cam was going to jump in.
There's also by the way,
Sorry.
just to finish, there's also a physical limit. The collisions in the LHC in the Large Hadron Collider are quite intense. And after 10 years or so, we will have destroyed the final quadrupoles, which are hit by the debris from the collision point. So at that point, we have to replace these final quadrupoles. And the idea is that we replace them with better ones to improve the performance at the same time, and not just build the old
So there's kind of a
magnetic.
performance-enhancing aspect over time as you get to know the machine, and then, but there are some physical limitations.
There's also some
as to
physical
how long.
limitations,
Yeah.
and then we luckily they happen at about the same time. So we make an upgrade which will give a higher data rate and also will maintain the functionality of the accelerator.
The message I get is that it's primarily driven by the particle physics needs, what the community actually wants to look for in the data. That would be your main motivation. I mean,
another limit if there's a competition, like I showed you the Tevatron collider in Chicago, it was turned off 1 year after the LHC had turned on, because LHC was producing at higher energy 10 times more data, and there was no reason to continue with the machine in Chicago, so it was not competitive anymore. That could be another reason to stop an accelerator.
So the comment I wanted to make, so Frank is of course completely right. However, the new thing is often, or most often, built on what has been there before. So the LHC, for example, reuses the whole proton accelerator complex at CERN, starting with the proton synchrotron, which was one of the first machines, and using the other things. There are then limits in operating those. For example, the technologies are too old. So we have the joules in the accelerator activity in the UK that Stuart was mentioning at Rutherford Lab, so ISIS, Diamond, and then of course the laser. Also in the north of England at the Daresbury laboratory with the electron accelerators there. So ISIS actually is older than, no, it's not older than me, but it's been going for longer than I've been going in science. And the early part of that is now a problem of maintenance because the things are not being built. So that's one reason. Those things have to be upgraded if we want to do the great science that is coming out of there.
Can I pitch in at this stage and say one of the short films we made in this Accelerators for Humanity series that Martin mentioned at the start is actually about upgrading that technology on ISIS, so do check it out afterwards.
Yeah.
Sorry, Ken.
So the other thing that we have to look at, and the kind of things that Stuart is doing is part of the solution but not all of the solution, is that the economics of doing this science is changing, and the copper and the ways in which we create the accelerating fields are quite energy greedy. They were created in the 60s and 70s when perhaps the cost of electricity was different. And so there's a whole theme there that we have to get to grips with to reduce the running costs of those machines.
Really good point. Yeah, which has spurred a whole lot more questions, it would appear. I didn't say who was first, so I'll come back over this side, I think. If someone could run a microphone down. Yes, thank you.
Yes, perhaps just taking up that point on economics. I mean, one of the great improvements in technology is obviously fusion reactors, and part of the offspin of what you're doing is the technology to make fusion reactors much better, and then the costs of electricity to everyone goes down, of course. But we were listening to a lecture about ITER, I think, about this time last year, and they were saying fusion reactors are perhaps 20 years away. Well, they've been 20, 25 years away for the whole of my lifetime. But it's the technology that, of the engineering that goes behind the particle physics, and the expenditure on that has got this tremendous offshoot to improve the engineering of fusion reactors. And I was wondering whether the plasma one in particular is an improvement on this.
So to me, just to interpret that question, to me the fusion reactors and accelerators are interrelated physics, but sort of a slightly different stream. Would you like to tackle that one, Stuart? Is that?
Yeah, I can have a go. My quick question would be, well, not a question, but my first thought would be, how do particle accelerators directly impact on fusion? Well, there's a couple of ways. So one is, so in a fusion reactor, as a plasma physicist as well as an accelerator physicist, I know I go to one or two seminars on fusion as well. So one of the things they do is they fire a beam of particles into a fusion reactor to make the plasma spin around and heat it. And so actually the very large fusion reactor ITER that's being built in Bordeaux, there is an equally large neutral beam accelerator next to it, which is quite interesting. Another thing that particle accelerators are going to impact on fusion reactors is there is in fusion you have a huge amount of neutron flux hitting the walls of the material of the chamber, and that gets damaged because of radiation damage. And so there are people looking at new materials to make the structures out of, and actually there are plans. I'm not sure where it's going to happen or if, but there's a machine called IFMIF, which is specifically designed for testing materials that are going to withstand really high radiation fluxes inside something like a fusion reactor. So yeah, there is a crossover between those.
I can add maybe something.
Please do.
Also, we have a strong collaboration between CERN and the ITER project, of course, for cryogenics and for the magnets.
Yeah, absolutely.
And in fact, our Future Circular Collider profits from the magnet development for ITER, because the superconductor Neutrinos was pushed for the ITER fusion project, and 600 tons. That was the first mass production of Neutrinos superconductor, which we want to use for the FCC. So we are very lucky, because now these companies have produced around the world material for ITER, and they are quite eager to now join and produce superconductor for the accelerators also. So we are lucky that we can follow up on this production.
Great. So there was, sorry, I don't recall if this person, was there one up here before? No, maybe it was in the front here. I'll get you next, yep, thank you.
Thank you. Suppose, this is a sort of an anti-accelerator question.
Devil's advocate.
Suppose I said to you that I could give you some higher energy particles without any accelerator, no energy use, you don't need to build anything, you don't need to dig up half of Switzerland to build anything. But the only problem is I can't tell you where it's going to arrive. So I'm talking about cosmic rays. I know you're going to say statistics, you won't get enough of them perhaps, but we can get higher energy, and you can just spend your money building a big detector, perhaps. Is it cosmic rays giving you higher energy now? Are they at all useful in this regard?
So maybe Phil, would you like to?
Thank you very much, Suzie.
You're welcome. I'm instructed that I'm not meant to be answering the questions tonight.
That's okay. So without doubt, the most powerful accelerators around are out there in the universe, and we don't understand how they work.
Probably plasmas.
But we can record on Earth cosmic rays arriving with incredible energies. I think, 10 to the, I've forgotten what the power is now, 16,
something like that,
17, electron volts, or 10 10 with 16 zeros volts equivalent of accelerated beam energy. And we don't really understand how those particles are accelerated out there in processes that are going on in black holes or whatever, centers of galaxies and so on. But they certainly arrive on Earth, and there are detectors on Earth which measure the impact of these cosmic rays. And so what we can do is we can count them. Okay, now that's interesting at some level, and you can make a graph, of number of cosmic rays versus energy, and it plummets down like this, and you can see some interesting features on the graph. But it starts to become very tricky when you get to higher and higher energies, because the area of detectors that you need to build in order to be sensitive to the highest energy cosmic rays starts to become tens of square kilometers. And that's sort of the size of the biggest arrays that we have on Earth at the moment. They're of the order of a few 1 to 10 square kilometers for collecting information from the cosmic rays, which basically amounts to counting them. Now, I'm not saying that isn't giving you useful information about the number of cosmic rays of high energy that are coming in, but that's not quite the same as what we try to do in accelerators, which is to make particles in the lab and measure them in the lab and understand their properties in microscopic detail. So it's a really, we're limited in the energies that we can do that by modern technology, but what we can do is make powerful and incisive measurements and really learn things at a microscopic level about what's happening. It's a bit trickier to sit on the ground with a massive detector counting these things coming in, and what you measure, of course, are the sort of secondary and tertiary products of these things hitting atoms in the high atmosphere and spraying products onto the ground. So it's a bit harder to sort of get at this fundamental information by counting particles that are coming in by mechanisms unknown out there in the cosmos. So it's not, it's very valuable science, but it's telling you things about astrophysics and what's happening in galaxies and stars and energetic processes out there in the universe, more than the microscopics of what matter is actually made of and what are the forces that interact between the building blocks.
So you could do it, but it would give you different science, is that?
It's complementary science. The cosmic rays are really telling you about astrophysics and galaxies and stars and black holes.
I think, sorry, you were going to pitch in at one point.
Yeah, well, but Frank also wanted to say something.
If I remember well, I think these max highest energy cosmic rays have energy 1 eeV, which is, I forgot, it's something like 10 to the 20.
I thought it was 10 to the 20.
Maybe it's 10 to the 20
it's a huge number.
And they cannot have a higher, I think this is limited by interaction with the cosmic microwave background scattering in outer space. And so, but these particles, when they hit the Earth, they can make some reaction with a fixed target on the Earth. But the center of mass energy in that collision, the energy available to produce new particles, I think, is lower than the energy that we have in the LHC proton-proton collisions.
Okay.
I'm not sure that's true, Frank, but
it's
never
similar.
mind. We can work it out.
It's not higher. No, if they hit a proton, energy is
if
lower.
If you've got a pen and paper,
like
you can tell us at the end, right?
We have 10 to the 12, right? So, well, maybe it's similar.
Yeah.
It's similar. It's not much higher, and the rate is 10 to the 42 times low. The flux 10 to the 42 times low.
Yeah. So you'd want to build a new one, right?
But still,
so that you can get a higher flux.
still, I have the ambition that we develop accelerators which can reach the same energy as a cosmic rays. Yes, certainly, that's one of the goals. We need 8 orders of magnitude to get there. Maybe with the plasmas, we make a big jump in that direction. Plasmas and crystals, we can get 4 orders of magnitude, and there's only another 4 orders missing to reach the cosmic rays.
He's ambitious, isn't he? Sorry, you were going to...
My comment was going to be, actually, we are looking at the cosmic ray sources. So with the neutrinos, there are obviously 3 neutrinos, okay? So that means there are 2 gaps. So I've got 3 neutrinos, I've got 2 gaps. With the experiments that I was talking about, you can measure the differences. So we can tell that what we call the second neutrino is heavier than the first, but we don't know if the third is heavier or lighter than those 2. Those measurements that are made with cosmic rays can in principle tell that difference. So we are studying that. It does have an impact on the terrestrial accelerator program. The measurements that Phil was talking about, they are getting really, really precise. So if you look at the data, it is over the last 20 years, it has become precise enough that the people are doing sky surveys of where these things are coming from. They are trying to correlate the different sources of particles coming to the Earth, so the optical astronomy and this cosmic ray astronomy and the neutrino astronomy, and now, of course, gravitational wave astronomy, so that whole thing is coming together. We need to understand the particles so that the astro part of our community is able to understand the universe. And because the universe is complicated and we don't understand it, it is not a priori the best way to study the particles. So we have to use that beam, if you want, where it is useful, and we definitely do study that. But then we need to make the measurements of the details that Phil was talking about in order to understand the universe, which is another fantastic goal.
Thank you. So we had one more question waiting just in here somewhere. Yep. Thanks, Martin.
The assembled panel have talked us through a number of technologies. But are there others not represented here tonight that it would be interesting to know about? Perhaps some work in Russia or Japan or somewhere else. Can the panel tell us if there is something that we're missing?
So I'm going to address that to start with, saying that most of the collaborations that are being represented here are fully international collaborations, as Phil mentioned. So I assembled the panel. So I'm the one who sort of chose which panel members we had here. Do any of you, would anyone like to put in, is there anything that you feel is...
As I accelerators on this chip, maybe that's somewhere between the conventional structures and the plasma, in between. So these microstructure devices, also driven by lasers potentially.
Yeah, so that's what I was going to bring up.
Okay.
Yeah. So this is where, so you can't use, lasers have really, really strong electric fields. I was talking about the electric fields in the plasma waves I generate being tens of thousands of megavolts per meter, but the electric field in the laser that we use to generate it is actually many teravolts per meter. It's just, it's not pointing in that, the laser's going in that direction, the electric field's pointing in that direction and oscillating, so you can't use it to accelerate particles. So it just also makes them wiggle around up and down. There is a way that you can take some of that laser field and make it point in the direction of the accelerator, and that's by putting it into a cavity. So it's actually very similar to the way when you put a radio frequency wave inside a cavity. So if I have a radio wave out in vacuum in free space, it's also, the electric field is just pointing perpendicular to the direction the wave is traveling, and it won't do any accelerating. By putting it inside a cavity, which creates a boundary effect, you actually get an accelerating field in the direction that you want. And there is a technique which is dielectric acceleration, or where you create very small channels in a high damage threshold piece of glass, basically, and that's effectively channels it's like a cavity but for lasers. So instead of using radio frequency, you're using laser frequency, but you're getting a longitudinal thing. I think there are I don't know a lot about it, so I don't want to talk too much about it, but there are, you could get very high gradients and things like that, but you're talking about accelerating a few particles in each channel at a time, so it's not obvious how you turn that into a high intensity beam that you need for a big particle accelerator, maybe.
So we're not hiding anything from you. If it were easy, we'd already have, accelerators taking us to the energies of these cosmic rays that are coming in. It's intrinsically very difficult. And so I think with that exception, I can't think of any other revolutionary technology that's out there that isn't actually being represented on the panel this evening. It's very hard.
So that's probably a good point to actually, for me to just throw in a question there, which is to say that most of these projects now, because we're talking about big science now, well, apart from maybe your lab, a little bit smaller, but very big projects, usually rather expensive projects, and usually with interest from all around the world, so they're normally very big international projects. So I thought I might throw the question at you of how do decisions get made in this international community? How does the structure work of, is it the guy who shouts loudest who gets their accelerator built, or maybe some of you who are more involved in that international decision-making process could comment. Phil, do you?
I'm happy to start, Suzie, thank you. Particle physics, accelerator science is genuinely a sort of bottom-up activity. The community is not that large. There are probably 20,000, I would estimate, particle physicists, accelerator physicists in the world. That's a large number, but it's still a well-defined community. There is genuine cooperation in our community. We genuinely, we've all worked together over the decades and so So I would say that fundamentally the discipline is bottoms up. People have good ideas. They try and sell those ideas to their colleagues. You try and gather a team of people to pursue these ideas. You ask your funding agency for some money to support some R&D, to do experiments and push technology and so on. If ideas look promising, bigger international collaborations form. The one that I'm privileged to lead has been going for about 15 years now. We have 50 institutes from around the world because people believe that this is a technology that really is very promising and it's worth them dedicating, their scientific lives to trying to make it work. And we've been able to achieve funding for the project. But of course, at some point, you have to move from an R&D enterprise to a real major facility that is actually going to be built. And those are, these days, billion pound, dollar, euro class facilities. And that's where it becomes a little bit more exciting, because then the world, of course, cannot possibly afford to have, if the money were unlimited, we'd have all of these things, right? We'd have electron, positron, proton, muons, and a super-duper plasma wake field accelerator. These projects are now of a sufficient scale and technical complexity and cost that it's very difficult to have more than one or two running in the world, and people come together globally to collaborate to try to realize and bring the resources together to realize multi-billion projects, and they get spread out over a long time scale. That's why you saw in Frank's slide, I think, 20 years gestation period for the Large Hadron Collider. And hence, you've got to run the thing for 20 years in order to fully exploit it and get all of the data and all of the information to make that investment worthwhile. So I think I'm straying from the question now, Suzie. Maybe I'll let somebody else have a go. But it's fundamentally bottoms up, and at some level, you've got to get serious, and you've got to get quite a lot of money, and that's when politics, of course, and global politics starts to enter into the picture.
Yeah, so maybe we can continue on that, actually, about the sort of the politics in the international community of science. There's been a lot of articles and information said about CERN bringing together people who might traditionally not have worked together and how that's had a positive effect. And I know you've all worked in very international communities, so would any of you like to comment on the sort of positive aspects of the very international cooperation that happens in this field? Maybe Ken, would you like to comment on that?
Yeah, well...
Or disagree with the statement?
No, I don't disagree with the statement. So I think CERN is a very, very special organization. So created in the 50s, when obviously Europe was recovering after the war. It's an international treaty organization. That's very special. I think to create the conditions in which such a treaty could be negotiated and signed, you would need special conditions, and they existed. The value of that is seen across the world, and CERN continues to attract more countries. And there's a negotiation period there because the treaty has to be agreed by all the other members, and you have to contribute to the budget, and that's an international treaty obligation once you're a member. So that brings an inertia, because clearly to get all the governments to agree to a treaty change takes time. But it's robust, because with the international treaty comes some kind of collective responsibility of all those governments that have signed it. And that's why CERN is as successful and as stable as it is. It is driven by science. What's the best science that can be done? And that actually, I think, is a unique combination of things. The international treaty organization, which is there to deliver fundamental science. That's a jewel in our collective crown, and we should protect it. So basically, I agree.
Maybe I can add that. I think that especially British accelerator physicists have made enormous contributions to CERN. John Adams commissioned the PS, and he built the SPS collider, and then Lynn Evans built the LHC.
True. So actually Britain has a proud history in...
Yeah, also Mike Lamont is leading the LHC operation. It's just a wonderful collaboration between the different nations of Europe and around the world. And it's working very well, the system. I think it's a kind of a model for successful international collaboration. Many people complain about the ITER and the fusion development, because maybe it looks less successful and not so efficient, but the CERN model is quite efficient.
Of course, though, we do live in interesting times with regard to European treaty organization. But it's worth pointing out that CERN predates the European Union by 3 years, and it's a completely separate international treaty organization. And so we're often asked, what does Brexit mean for the UK's involvement with CERN? Well, hopefully, to the extent that Her Majesty's government continues to pay our subscription to the international organization, we will continue to be full members of CERN, and as Frank has very generously said, play a very important role in this greater entity.
Great. So we've only got a couple of minutes left, so I'm going to ask if there's maybe one more question from the audience before I wind up. Is there one more going? There's one right up the back in the middle, I think. If I can... You're just below a light, so that was very difficult to see. There we go.
Gosh.
Hello there. I was wondering, for the electron colliders, you have the electron and positron colliders. Is there any muon, anti-muon, or tau, anti-tau colliders that exist? And if there are, is it perhaps influential in this discovery for a new powerful collider, for instance?
So do any muon colliders exist?
No, they don't. So people have made muon beams, many muon beams around the world. A muon beam at Rutherford Appleton Laboratory, for example. The difficulty is making the beams intense enough. So I had a slide which was intense cold muon beams. Cold is a jargon for this small beam. So if you want to get collisions at a large rate, you have to have either an enormous number of particles, or you bring them into a tiny, tiny spot. So both ILC, CLIC, FCC, they will all make the particles into a tiny, tiny spot. So to do the neutrino science, you need a cucumber of particles. If you want a muon collider, you've got to have something less than the thickness of a hair. That's the size of the beam that has to collide. So the difficulty is that you have to reduce the size of the beam such that you can get enough collisions, and that's what this cooling business is about, that we're building the experiment at Rutherford Lab, and we need to demonstrate that technology, and then we can discuss making the muon collider.
Okay, so I have one final question for each of you just before we leave, which is for the younger people in the audience tonight, or for those who are particularly interested in this field, would you have any advice for people who might be interested in working on these future machines that might come along in, very soon, or 10, 20 years' time, 40, 50 years' time? Any sage words of advice before we go? I'm going to start on this end. You've got...
Well, sorry, the trite answer in the UK is, of course, that you've got to do physics at A level. And especially if you are a female member of the audience, we desperately want you to do physics at A level. And I can see there's a budding accelerator physicist on the front row here. Physics at A level, go and do your physics degree. Go and get a summer intern at CERN, for example, and go and spend 8 or 10 weeks during your summer vacation working on a project at CERN. Get excitement, get fired up, and then come to the John Adams Institute and do your PhD.
Frank, anything to add to that?
Yeah, I'm doing accelerator physics since 27 years or so. I did my diploma thesis and then PhD, and I always stayed with the accelerators and colliders, and I enjoy it very much. You can do all kinds of things. You can be in the control room playing with the beam and optimizing the operation.
Can I just check, do you actually get to control the LHC? Is that part of your job?
Not at the moment anymore.
Not at the moment, but you have.
Past, yes.
Cool that. Well, sorry.
For some experiments, we can control the LHC, yes.
So it's a fun career.
Yeah, you can do computer simulations. I do a lot of computer simulations. You can do analytical calculations, and you're more or less free to choose. And I like the combination. It never gets boring. Huh? I can spend some day in the control room with the operators. I can spend another day in my office doing simulations, or I can have meetings or whatever. But you can do many different things. So you are more flexible than many other fields of physics, I think. Yeah. And we need more accelerator physicists. We have never enough applicants for doctoral students or for postdocs. we never find candidates. We have many more posts than applicants. So anybody who studies...
If you want a job at CERN,
so
now you know.
I must say, yeah, it's very difficult. They're oversubscribed. Last year, the postdocs were oversubscribed by a factor 10 almost. 10 different groups asked for the same candidates because there are so few candidates.
Wow.
So that's why FCC is not faster, because we cannot get all the postdocs that we need.
So we need smart people. Yeah.
And then maybe the time scale is a bit worrying. You don't want to wait 20 years for the next machine, etc. But I enjoy it very much. I can always work on an operating machine, work on the next generation, and also look at the generation beyond the next. So I like this very much. And you can learn. You always learn from the existing machine what to improve and what to do better for the next.
Long-term.
Yeah, you can do the things at the same time.
Yeah, that's a good point, actually. Yeah. Anything to add over this side?
I might just add one thing. Sorry.
Yeah, go ahead.
Which is that, so one of the good things about doing plasma-based accelerators, certainly as a PhD student, is the timescale of the way things are moving is much faster. So and the experiments are much smaller. So you almost get to own a large part of a project all of your own, whereas if you get involved in very big machines, you can be very, very focused on a really important part that's making a big contribution to something very important, but it can get very detailed, whereas I think when you're doing the plasma-based stuff, it's quite fun, because you do everything from building the machine to designing it with simulations to doing all of the data analysis and stuff. It's all on your own, so it's kind of fun like that as well. So.
And not to be left out, Ken, anything to add?
Well, so I've been thinking. So it's I'm going to say something which is personal, which I never really do. I have two daughters, one of whom is genuinely considering particle physics, and therefore this is a real question for me, not an academic question. And what I say to her is, follow your heart. And I've had a great time, right? I've never done a day's work in my life. What I do beats working for a living. Really great. If she falls in love with another area, follow that, because that's what will make you work. Particle physics, accelerator science, it's fantastic. If you love something else, do that.
I think that's a nice point to end on. Do what makes you happy. And I think for the panel down here, working on accelerators has made us all, given us all a really enjoyable career. I'm obviously, just starting out in my career in accelerators, and I certainly enjoy it for many of the elements that you've said. So just to wind up, I'd like you all to please give a massive round of applause to my illustrious panel. Thank you.